All right, guys, let's go ahead and let's start talking. Let's do a little refresher on our topics of the sampling distributions, okay? So, the first key thing, guys, is to make sure you understand the term and the shape of and the qualities of the population versus this thing called a sampling distribution. Okay, so the first thing is we need to know what's the population versus the sampling distribution. Okay, so I have this here. This is showing three shapes. And we're going to have somebody tell somebody something of what's the population and what's the sampling distribution and that kind of thing. Okay, so I'll go ahead and tell you here's kind of a zooming in. We've got this picture here. This has got the individual X's in it. This one underneath it was created from samples of size 2. So that was a random selection of 2 of the X's dropped down. And then here, this is from a random selection of 25 and then dropped down and you get your X bar. Okay, so real quickly, let's see who's going to tell somebody something. Evens, tell the odds. Which of these things is population versus sampling distribution? Go. Evens telling the odds. Let's see here. All right. Evens told the odds, so the odds tell me. Preston, what'd you come up with?
Well, that top one's the population, and then the next one is like you take a sample from the population.
Yep.
And you average it all together or something.
Okay, correct.
You have even more from the population, and then you find the averages of that.
Okay, good. So that is correct. But by name, I want you to know that this top one is the population, okay, which you said, so that's good. That this second one is a sampling, it's called a sampling distribution. Okay, so you need to know by name that actually both of these bottom ones are sampling distributions. This first blue one is made up of samples of size 2, and this second blue one is made up of samples of size 25. Okay, next thing. Let's see, that was evens. So odds, tell the even the relationship of their centers. How are the means related on all three of these shapes? Go. Odds telling the evens. How are the means related on all three of these shapes? Okay, yeah, so that's all I'm actually looking for is something real simple. What do you have to say about all of these means? They are the same. Okay, so they are the same. Now, it's quite obvious on this shape. Might not be as obvious on something such as this. So let's investigate this. Our population is skewed which way? Population is skewed to the right. This second one that was samples of size 2 is better. However, it's what? Still skewed to the right. This last one is large enough size samples. Technically, it's supposed to be 30, but this applet just does 25, and so it is unimodal and symmetric and somewhat normal there. Okay, so let's investigate the centers here. This one has a center of 8. This bottom one this middle one has a center of 8, and the bottom one has a center of 8. So even in the shapes that are not unimodal and symmetric, the centers are still the same. Okay, so that was the key. So regardless of the skew, the centers are still the same. Now let's talk spread. What are we going back to our one that is symmetric shapes, unimodal and symmetric? What do you have to say about their spread as the n gets larger? Where are we to? I think we're to evens tell the odds. Go. Evens tell the odds. What's happening as the n gets larger? Go. Okay. What do you say? The spread is getting Smaller. Okay, and odds tell the evens why that's happening. It might help you to know why because of, based on this formula here, go odds, tell the evens why it's getting smaller. All right, I think you got that. Let's do a specific example. Okay, look here. The population standard deviation is 5. See the symbol I used for that? Population standard deviation is 5. Now, this first sampling distribution, see it's the standard deviation of, see look, I have a little X bar right there because it's the sampling distribution standard deviation. It is the population 5 divided by the square root of 2. And that's smaller. That's 3.53. Let's look at the last one. Here is the population standard deviation of 5 divided by the square root of 25, which is 1. So you're seeing that as n is increasing, that spread is getting smaller. Okay, and that identical thing is happening whenever it's a skewed shape as well. Real quickly, you can see, look at what happens when you had here's a uniform shape. You can see what samples of size 2 did, and then the large enough samples. And then here's a super funky one. There's a really messed up one. The samples of size 2 is still messed up, but the large enough samples, nice. Okay, let's do your assignment now. Let's go over page 46 to 48. Here we go. Okay, so first things first. Okay, so if you had missed Friday, that was one of the main things that we talked about on Friday was those qualities we just discussed. The other main thing was the conditions that have to happen for that magical unimodal symmetric somewhat normal model to apply. And those are, so let's read this problem here. Here we had 7% of the people who received loans will not make payments on time. The bank has approved 200 loans. Okay, so is this first off, how do you know if you have a mean problem or a proportion problem? Proportion problem.
Proportion if you have like a percentage, right?
Yep, that's it. Proportion problem. They gave you a percent, and they gave me the percent of 7% of loans. Okay? Yep, there it is. So there's your proportion. So the population P is 0.07 with a sample size of 200. Now here comes the conditions. They ask us to check these. Okay? So and sometimes these are called assumptions because we don't know them for sure. We're assuming these to be true. And upon them being true, we can do normal model math. So here we go. So you have to write the word out random, not just RIL, and use context. So random, I'm going to assume these 200 loans are randomly selected from all loans. Okay, independent. So the song and I'll sing you the song as we go along because that might help. So random, stated, or assumed to represent the population, independent, N is less than 10%. Of the population. So here's my independent. 200 loans are less than 10% of all such loans. Okay. Large enough is tricky because it all depends. Mean or proportion. So the large enough has a certain rule for the mean problems and a certain rule for the proportion problems. And I've written it up here. Up here at the top. Look at this large enough. Depends if you're a mean problem or a proportion problem. Mean is 30. So sample size has to be greater than or equal to 30 for means. Proportion is 10. And that's where the successes are at least 10 and the failures are at least 10. And you show these maths. So look here. Here's how that looks here. Large enough is tricky because it all depends. Mean or proportion. This is a proportion problem. So I have N times P, which is 0.07, that's 14, and yes, that's greater than or equal to 10. And N times the failures rate, 0.93, that's 186. That is greater than or equal to 10. Yes.
How do you know that 200 is less than 10%?
So that's a good question. Okay, so that's why these are frequently called assumptions, because we're basically saying on the assumption that these hold true. So here's the criteria that needs to be met, and if that is met, then here we go. Okay, so FYI, for those of you who weren't here on Friday, I want to remind you that N is less than independent. By us having a small enough sample, it doesn't affect the probability, but it is large enough to meet the criteria to make it unimodal symmetric and approximately normal. So, so then the song says, and the normal model applies now. But we want to make sure we say approximately normal, because we do not know that it's the actual function of the normal model. It's approximately normal model applies. All right. So there's that. Now, what are the mean and standard deviation? Okay, so we remember that the center is going to be the same as that population, 0.07. Okay, I had a really good question last period, and they asked, why is it not 14? Okay, and that is because we want the mean of the proportions, the mean of the p-hats. Okay, the mean of the p-hats is a proportion number. This here would be the average number of items. Okay, and we're going to do a distribution of sample p-hats. Okay, and then there's our formula for standard deviation. All right, now let's think about, okay, so this question is asking about over 10% of the, what's the probability? Over 10% of these clients will not be making a timely payment. So, but I want us to take a look at this picture real quick. Okay, so do you remember last Thursday when you were here for the lab? You all had a sample and you all got your own p-hat sticker. Let's have evens tell the odds what your p-hat sticker represented last Thursday when we did our M&M stuff. Okay, go. Evens tell the odds what your p-hat represented. Yep. So over there on the board, I have it over there. Over there on the board, every single one of you got your own proportion of 50 M&Ms that are blue. Okay, so that was your p-hats. And you put so in this case, every single one of these p-hats is the proportion of 200 randomly selected loans and the people of those that do not make their payments on time. Okay. And so this question, so when I want you to draw a picture, draw some p-hats in there and show where this is centered. So most of the p-hats are going to be, most of the proportions will come out to be about 0.07. You know, you get 200 loans and you randomly select 200 loans and you randomly select 200 loans and so on. But they want to know what's the probability you get one of these p-hats over here in this section here. What proportion of p-hats are up here in this section above 10%? That's what it's asking for. So then we z-score that puppy in norm CDF to get that area. So you got your p-hat minus the p over the standard deviation of p-hats, and that's your z-score of 1.67. You norm CDF it, and you get that. So about 4.78% of all of those p-hats, of all of those samples of 200, had more than 10% of people not making their payments on time. Okay. All right, so I hope that was good enough to kind of get the ball rolling. And so this next one, the typical place that we struggled was identifying what the p-hat was. So let's talk about this. And this is, I love this problem. This one is like, you know, they truly do this when they're going to do medical experiments, okay? So this was a problem where they said, okay, we know about 4% of newborn babies are going to have this particular gene that we need to analyze. All right? So let's take a sample of 732, and I hope that gives us enough babies to examine. They're hoping to have at least 20 babies to be able to identify and then track. Okay. All right. So the thing that lost people on this one is that the p hat is that you're looking for is 20 over 732 or higher. So let's just go. I'm just going to go ahead and do this to 2 significant digits. So we want to, our goal, so the researcher's goal is to get 20 out of 732 or higher. Okay. So that's ultimately we're going to be looking for. And where should all the p hats be centered? At 0.04. Yeah, population p. Okay. So the first question is to go through the conditions or the assumptions. Random is stated or assumed to represent, or assumed that it is randomly selected. So I'm assuming. Okay, and so criteria to get this correct, write the word random and say we're assuming 732 newborns are randomly selected. Context and the full word. Okay, context and the word. Word. Okay, independent. Independent. N is less than 10% of the population. So I wrote the word independent, and this is so that it's not big, it's not too big. It won't change the probability. 732 newborns is less than 10% of all such newborns. You're going to find this word such is magic because it kind of basically glumps all the criteria you need all together and says, oh, you know, the kind of newborns we're talking about, the ones in this region or the American ones or whatever, all of the same kind of newborns. Because maybe do you think some genes differ from, race to race, or maybe even like part of the world to another part of the world? I think so. Okay, there's like higher proportions of certain things. Okay, large enough is tricky because it all depends. Mean or proportion. Is this a mean problem? No, it's not. Mean is 30, but here's proportion is 10. So I need n times p and n times 1 minus p to both be greater than or equal to 10. And the normal model applies now. Approximately normal model applies. Conclude. So that's the necessary requirements to state for your conditions and assumptions. All right, your mean and standard deviation. There you go. Mean is 0.04. Standard deviation I computed from the formula. Okay, that formula does not have to be memorized. It helps if you know it because then you can just do it quickly, but that will be given to you. Okay, you don't have to have that memorized. Now, what does each p hat, so when I draw a picture with a whole bunch of p hats in it, what does every single one of these p hats mean? Okay, so we're going to have odds, you're up. Odds, tell the evens what every single one of those p hats in there represent. Go. Okay, so odds told the evens, so the evens tell me, Logan, who's even over there? Okay, what you got? Yep, perfect. Okay, so that's actually what I have written here. The proportion of 732 newborns that have that particular gene we're identifying that what contributed to linked to juvenile diabetes. So every p hat in there. So the question is, up here at the top, what's the probability that they find enough subjects for their research? And they need at least 20 subjects. So they need this situation here, 0.027 or more. Okay, 0.027 or more is what they need. And so then that's our p hat. that we're looking for is our 0.027. So there's my z-score. P hat minus the p over the standard deviation of p hats. Okay, and then I'm going to do my little z-score. P hat minus the p over the standard deviation of p hats. Okay, and I get negative 1.81. If you just used 2 decimal places, then you got negative 0.81 for your z-score. And so then a norm CDF, greater than that. And depending on where you rounded, when I had rounded to more, I got 95.99, 96.5 if you did negative 1.81. Anyway, so essentially, what then can the researchers conclude? When they have a sample of 732, there's basically a what? Pretty much a 96% chance that they're going to get at least 20 out of that 732 that have the gene they need. So there's about 96% chance they're going to have enough babies, newborns, that have that gene that they need to follow in their research. Okay? This is legit. Truthfully, that's what researchers would go through the process and do. Did you write down that right over there on the board so you had so you know what that is? Okay. So, all right. So that's going over the first 2 problems of your homework that were really like the technical, doing the mathy stuff. Now, here's some theory. Okay, so here's kind of just in theory what is happening. All right, so let's take a look at this. Here we go. All right, so, okay. So here we have a sample is chosen randomly from a population that can be described as the normal model. Okay, so you think that you're just kind of reading a sentence and it's not a big deal, but there's really 2 key pieces of information in there that make you, that are important that you kind of like hone in on. What do you think those 2 pieces of information are? Ones that are underlined. Man, you are just freaking genius. Okay, yes. Okay, so the things that you should hone in on when you read something like that is, number 1, they're telling me the population is normally distributed. Okay, so if they're telling me that the population is normally distributed, then my brain should be thinking of this situation right here. Okay, so that's why that was important. That tells me the population is normally distributed. Therefore, talk to me about any sampling distribution that comes out of it. One that's small samples, what shape will it be? Okay, normal. One that's large samples, what will it be? Shape. Yes, okay. And you know they're all going to be centered at the same center and so on and so forth. Okay, so that's what plays into this problem here. So let's go through the question. What shape will the sampling distribution be? When we talk shape, I actually try to caution even myself. I get caught in this saying this. I shouldn't describe a shape as normal. A shape is unimodal and symmetric because the word normal is actually like that mathematical function, normal model. Okay? All right. Where will it be centered? Where is the center of these sampling distributions? The same as the population. Very good. Okay, same center as the population. All right, how about the standard deviation? I went ahead and I just put the formulas down, so that's the spread that you would have. Okay, and then the next question is asking what's going to happen to the shape of the sampling distribution. Okay, so you hear that? What's going to happen to the shape of the sampling distribution as your sample size gets larger? Okay, what 2 shapes here are the sampling distributions? The blue ones, sampling distribution. Vocabulary, sampling distributions right there, the bottom 2 ones. What happens to their shape as the n gets bigger? Spread gets smaller. Good, so that's what you're saying. So their center stayed the same and they become less varied. Their center becomes the same and they get less varied. All right. So there was that. Now, similar type questions here, but look at what happens. What are we dealing with? A population, so that's our starting point, a population that is skewed to the left. Okay, a population that is skewed to the left. Okay, so that's your key that you should have noticed. Okay, population being skewed to the left. Now, I have a picture here that's not skewed to the left, it's skewed to the right. Okay, but think about what's happening here. Tell me about their centers. What about their averages? All the same. Tell me about the standard deviations as n gets bigger. It's also going to get smaller. Okay, but tell me about the shapes. The first sampling distribution with n is 2 is what? It's better, but still skewed. But tell me about the bottom one where the sample size is large enough. Ding, ding, ding. Unimodal and symmetric. So here we go. Let's do these questions. So what happens if the sample size is small? Then it will, in this case, we were talking skewed to the left. It is still skewed to the left, even though the picture I showed you a moment ago was to the right. This one is talking about skewed left. I just didn't have that picture. Okay. What about happens if we have it? Oh, you know what? My bad on this because, and I just realized this today. I've been doing this worksheet for this problem forever. And it says, describe the sampling distribution. So I just did shape. What did I miss? Yeah, center and spread. Socks, but we don't really talk necessarily outliers. So socks, I should have done shape, center and spread. So the shape is still skewed left. What about the center? Same center as the population. And then what about the spread? It will have a smaller spread than the population. Because remember, no matter what n is, it's still going to get smaller spread. Okay. Next, what happens if the sample size is large enough? What will the shape be? Unimodal and symmetric. Don't say normal. Normal is a mathematical function. The shape is unimodal symmetric. What's the center going to be? Same as the population. What's the spread going to be? Even smaller, even littler. Going to get littler and littler. Okay, that's a fun word to say. It reminds me of Patrick going little, okay? Littler and littler. Okay. All right. Moving on. Okay. So I think I have something missing here because I think there's a couple of good things you can say. What happens as the n gets larger, as the sample size gets larger? What happens to the shape? Oh, wait, hold on. It just says what happens to the distribution of the data in the sample. So what's the shape going to do? What's it going to do if as n gets larger? More symmetric. Ding, 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 ding. And I didn't write that on here. So the shape will get more symmetric. Okay, and then, but what do we know about the spread? It will get smaller. How about the center? What's going to happen to the center as n gets bigger? It stays the same. Center stays the same, FYI. Okay, good job, guys. Almost done here. So, here we go. Obviously, okay, so look here. Assume that the duration of all human pregnancies, population, can be described by the normal model. Okay, so at this point, your brain knows the shape of it, okay? And we know that it has a center at 266 days with a spread of 16 days, okay? You should now also know about every single sampling distribution that comes out of it will what? Unimodal and symmetric, approximately normal as well. Okay, let's see. What's this first? Okay, so this first one asks about pregnancies. So this is from the population, the proportion of all pregnancies that are between 270 and 280. So this is just like back from October, regular old, finding your two z-scores and finding the area between them. The thing I want to draw your attention to is the standard deviation I used was, indeed, the population standard deviation. See right here? Population standard deviation of 16. That's going to come in. I'm going to really point that out because later it changes. Later we use a different standard deviation. Okay. Now, the next one says, how many days should the longest 25% of pregnancies be? What's that? That's going to be out of the population, yeah, but it's also, is that going to be the top 25%, the bottom 25%, the middle 25%? What? Longest 25% of pregnancies. Top 25%. Now, does that 25% mean 0.25 is a z-score? No, it does not, because percent is not the z. It's not the z. You use percent to get the z. And when I use the percent to get the z, use area below as the percent. Okay, so inverse norm of 0.75. It's 0.67, and then solve for x of 276.79 days. Okay, those two problems are straight from stuff from October. Regular old normal model. Good old chapter 6. Okay? All right. Here is where the new stuff kicks in. We now have a clinic who is providing prenatal care to 60 pregnant women. That means sample of size 60. Okay, so now sample of size 60. So my first question is, tell me about the distribution of this sample. Tell me the shape of it. Unimodal and symmetric. There are two reasons you know it is unimodal and symmetric. So you're going to have to think right now. Shape is unimodal symmetric. I don't know who we are to, so I'm just going to do a new draw. Here, let's go. Evens. Tell the odds. Two reasons why you know this shape of this distribution of samples of size 60 is unimodal and symmetric. Go. Two reasons. Okay, what do you think? Population right here. And if the population is, see, look, if the population is, then anything that comes out of it is. Okay? All right. So let's see what you came up with. That was evens telling the odds. Okay, so odds back there. Cheney, who's odd? Okay, so you tell me one of them. What's one of the reasons that you know the shape is?
That 60 is bigger than 30.
Okay, good. Good. The n is greater than or equal to 30. It's at 60. And Hannah, what's the other reason? Yep, right here. Yeah, we already knew that the population was normal. And hello, people, when the population is normal, then anything that comes out of it is also going to have that shape. Okay, what's their center going to be? Same. So it'll still be centered at 266. But what about the spread? What's the spread going to be for this one? Is it going to be 16? No, it is not. So that's one of the things that I want to point out to you. Let's see here. Let me get this going here. Okay, so let's see. Okay, so let's take a look at what we got going on here. This thing is okay, so the center is still going to be centered. Let me get this. The mean of the X bars is still going to be at, what was the mean up above? 266. The mean is still going to be 266. But the standard deviation Guess what? It's not 16. The standard deviation, see, look here, they're both going to be centered at 266, but the standard deviation is smaller. The standard deviation is now what? Whatever the one was before. What was the one before? 16. And then what? Down here, right here. The standard deviation is smaller. 16 divided by the square root of 60. Okay, and so that's what makes this problem different mathematically, is that the center is still 266, but the standard deviation is not 16 anymore. Standard deviation is now 2.06 or 2.07 because it's 16 divided by the square root of 60. So that's how you get your answer, and it's about a whatever percent chance, 2.2% chance. Okay. All right. So there was the kind of review of everything we learned on Friday and going over the assignment. I hope that helped. Do you think that's clearing up things a little bit better and like really re-emphasizing what things are important and what you need to know? So I want to now take a look at the assignment you're going to do. We're going to do a little bit of it together. Okay, so let's take a look at your assignment is going to be here. Starting, okay, this page 35 is another one of those notation matching ones. Okay, so that's another practice. Page 35 is a notation matching. Okay, because that will be on your quiz. And then 53 to 56, and then the warm-up is on page 57. But notice I have two problems to omit. So omit problem number 29, which is a half of a page, and problem number 41, which is another half of a page. So you're getting to omit basically one page out of that. Okay. The reason is that those have to do with stuff from chapter 16, and right now at this point we're not ready to kind of pull that back yet. Okay. So I actually want to take a look at the bottom problem on this page. Go to problem 17, and I want you to read it to yourself, and I want you to determine first and foremost, what is the population we're going to generalize to, okay? And then figure out what the population P, the P hat, and the N are. Okay, so let me give you about 30 seconds or so to go through that and think about it, okay? Go. So what is the population of this problem? What's the entire thing we're going to make an assumption about based on one sample of 150? Yes. Okay, good. The population. So this is like when we had Rita on the Lay's potato chip problem, and the guy was like going on top of the potatoes. You remember that? The guy going on top of the potatoes. They were going to make a claim out of the entire shipload, the truckload of potatoes based on that one sample of 150 pounds. Here, the population is all the apples on the truck. Okay, and they're going to decide to reject or keep that entire truck based on a sample of just 150 apples. Okay? All right. Now here's the catch. What is the population proportion of apples that do not meet the desired standard? Is it 0.05 or 0.08? Okay, discuss amongst yourselves. I hear both answers. Which is the population proportion of apples that don't meet the desired standard? I still hear both answers. Okay, so what are we going to say? Everybody call it out. Ready, go. Okay, I hear both, but the answer is, in fact, 8% of the apples on the truck do not meet the desired standard. So that's the population, the truck's amount. So the population P is 0.08 because that's the facts about the truck. Now, the farmer is certainly hoping he can pull a fast one on the factory, and they find a sample that is a 5% or less. Do you think some of the samples that they could get could indeed show 5% or less? Probably. Okay, so let's take a look at the top of the next page. Okay, so let's see here. All right, so here's a picture. See this? I drew all of these P hats. Okay, and they're centered at 0.08. What does every single one of those P hats represent? Odds tell the evens what every single P hat is. Go. Okay, every single P hat is a sample of 150 apples and the proportion of them that are defective. Sometimes more than 8%, sometimes more than 8%, and sometimes less than 8%. But on average, because the truckload has 8% defective, most of them will be around 8%. Okay, but the question here says, what's the probability that the shipment will be accepted anyway? That means, what's the probability that they get one of these P hats down here that has less than 5% defective? So down here, then the farmer gets to pull a fast one on the factory and gets to give them his truckload of bad apples because they think they're good. All right, so we're going to we know that the mean is 0.08. Standard deviation, we're going to follow this formula here. Okay? And then I'm going to do my z-score, p hat minus the p over the standard deviation, and then do that lower part. Okay. I'm going to leave that with you, but then I'm going to do one more problem with you so that I think if I go through this with you, then you're going to be able to kind of follow what's happening in this whole chapter. Or this is the last one, and then I think you should be good on this assignment. Here we go. So I have pictures drawn here, but they are not the answers to this question. These pictures are for us to help understand what's going on. Okay, so this question is about people that work in business or work at their job. Some business analysts estimate that the length of time people work at a job has an average of 6.2 and a standard deviation of 4.5. Explain why you think the distribution filled with individual times. So that means here is one person and how long they were there. Here's a person and how long they were there. I was at my first job about 7 years. So my first teaching job, so I was about average, so 6.2. However, why do you think that this shape is going to be skewed to the right? Do any of y'all have any of your parents? Here I've worked 16 years, but my father-in-law, he worked at the same job. He started and retired at the same job. Okay. So, not a whole lot of people do that. That's why he's an outlier up there, up there. But so you're supposed to explain why the distribution is shaped like this. Okay. Second, look here at this second shape on part B. What would happen if I take samples of size 100? What should samples of size 100 stimulate in your brain? Ooh, samples of size 100. Ooh, that's large enough. So an average of 100 follows this unimodal symmetric normal model. But wait, the question is, come on, I got 1 minute, so chill your boots. The question on this part B is, why would you be allowed to estimate finding an X bar in average above 10 years here, but not on the one here? Not here, but I can do it here. Why? Okay, and so then there you go. All right, I will see you tomorrow. We'll go over some stuff and be ready for a quiz.